we're going to talk about terminal speed and terminal velocity. So here we have Marilyn Monroe. She just jumped out of an airplane and she is in the atmosphere. Because she's in the atmosphere, we're going to take into account wind resistance in this problem. The instant Marilyn Monroe jumps out of the airplane, she's not yet moving. And because she's not moving, she has no wind resistance acting on her. Imagine rolling down the window of your car and sticking your hand out of the car window while it's not moving. If you stick your hand out of the car window when it's not moving, you'll feel no wind resistance acting on your hand. The second you start driving, you'll start feeling the wind pushing back on your hand. That's wind resistance. But as long as you're not moving, wind resistance doesn't act on you. And as long as Marilyn Monroe's not moving, she has no wind resistance acting on her. Only gravity acts on her the instant she steps out of the airplane. For this problem, I have said that the positive direction is down, and the reason that I say the positive direction is down is because Marilyn Monroe is moving down. It's usually convenient to say the positive direction is the direction of motion. Okay, so the instant Marilyn Monroe steps out of the airplane, she's not moving, so wind resistance is not acting on her at all. The only force acting on her is the force due to gravity, and we know the force due to gravity is just her mass times g, and g is 9.8 meters per second per second. We also know that the force due to gravity always points down towards the center of the earth. Since the force due to gravity is the only force acting on Marilyn Monroe the second she jumps out of the airplane, we know that the net force acting on her is just the force due to gravity, or mg. Remember, this sigma F just means net force or total force. Since the total force acting on Marilyn Monroe points down, her acceleration also points down. That's Newton's second law, right? And since the net force on her is pretty large, her acceleration is pretty large. So at this point, the instant Marilyn Monroe steps out of the airplane, she has a relatively large acceleration downward. 1 second after Marilyn Monroe starts to fall, she's moving slowly. So imagine sticking your hand out of the car window. Your car is moving slowly. You will feel some wind resistance acting on your hand. It'll be a small wind resistance, but it's there. So when Marilyn Monroe is moving slowly, there is a wind resistance acting on her, and we abbreviate that F little f. It's just a frictional force. And we've drawn this yellow vector to indicate the wind resistance acting on her. Notice the wind resistance is relatively small compared to the force due to gravity. I want you to also notice that the wind resistance is pointed upward. We know that friction is always pointed in the direction to oppose motion. It always tries to oppose motion. So since Marilyn Monroe is moving downward, wind resistance is pointing upward. I want you to notice she still has the same size force due to gravity acting on her. That hasn't changed, and it won't change as long as she's at or near the Earth's surface. The force due to gravity will always be mg acting on her. But what we're really concerned about is net force. So to find the net force, we just add up this yellow vector and the red vector. Since the two are pointed in opposite directions, we add them by subtracting their magnitudes. So the net force, I would say, would be about this length. And since the larger vector points downward, her net force will also point downward. So her net force is smaller than the force due to gravity. So what does that mean about her acceleration? Since her net force still points downward, net force is something like this. Since her net force still points downward, her acceleration is still aimed downward, so she's still speeding up as she falls. But her acceleration is smaller now than it was when she first stepped out of the airplane. So she's not speeding up as quickly as she was the instant she stepped out of the airplane. So a few seconds after Marilyn Monroe starts to fall, now she's moving more quickly. Because she's moving more quickly, the force due to wind resistance is larger. So imagine sticking your hand out of the car window when your car is going more quickly. The wind resistance pushes back harder on your hand. Same thing with Marilyn Monroe. When she's falling more quickly, wind resistance exerts a greater force on her, or is a greater force exerted on her. It's still pointed in the direction opposite her motion. Notice there's still a gravitational force exerted on Marilyn Monroe. Notice it still points downward. But her net force now, if we add up the wind resistance and the force due to gravity on her now, the net force acting on her now would be something like this. So her net force is quite small now. So that means that her acceleration is also quite small. Since her net force points down, her acceleration also points down, so she's still speeding up as she falls down, but she's not speeding up so quickly anymore. Again, her net force is smaller than it was when she stepped off of the airplane. So now she's still accelerating downward, she's speeding up downward, but she's not speeding up quite so quickly. A few more seconds later, Marilyn Monroe is falling really quickly. Because she's falling really quickly, the force due to friction is really big. In fact, at this point, the force due to friction is equal in magnitude to the force due to gravity acting on Marilyn Monroe. So at this point, the net force acting on her is zero because the two forces exactly counteract one another. At this point, since the net force acting on her is zero, she's not accelerating anymore. Now that doesn't mean she's not moving, she's just not accelerating. She's not speeding up anymore. At this point, she's reached what is known as terminal velocity, or if we express the velocity without a direction, we call it terminal speed.